Great. Thank you so much, Audra. Hi, and thank you for joining us today. I'm Camille Schrader. I'm product marketer for geotechnical engineering, and I'm just going to be sharing a quick overview with you before we get started. We're going to be hearing today from Richard, who will be sharing how to master the most challenging convergence issues associated with dewatering and how Plaxis 2D can address these challenges. So as a geotechnical engineer, you seek reliable solutions that support your designs, and you need applications that provide data information and analysis support, reduce risk, and are easy to use while saving you time and money. Excuse me. Plaxis, Open Ground, and Soil Vision work together to ensure you have access to geotechnical data and analysis to support your safe solutions and data-driven decisions. With our applications, you can overcome the challenges presented by the infrastructure, mining, landslides, dam and levee, tunneling, offshore, rail, and oil and gas industries, and the various other solutions as shown. You can design and construct large infrastructure projects in a cost-effective manner while reducing risk and increasing safety during the project's life cycle. And we take pride in our applications. We ensure these three main pillars here. Trusted information. You can plan digitally faster, anytime, any place, in many ways. And driving efficiencies. Intuitive workflows allow for easy design of 3D conceptual models coupled with multidiscipline digital workflows. And lastly, advanced expertise, analyze with sound computation. Our applications offer data integrity and leading capabilities of 2D and 3D analysis for both finite element and limit equilibrium. And digital twins can span the entire asset lifecycle, starting as a project digital twin and eventually becoming a performance digital twin. Here we want to take a closer look at some examples in geotechnical engineering workflows. So our Bentley Geotechnical Engineering is going digital from ground to cloud. You can plan, design, analyze, construct, and operate with new digital workflows for improved efficiency and interoperability. Today, we're going to be covering the analysis step as we see how you can efficiently model groundwater flow and dewatering for excavation problems. And we'd like to kick off our webinar and hear from you, our user. So now at this time, we have a quick poll to get everyone started with this interactive webinar. So you can choose your answer and be sure to click submit in the poll question window, not the question box. So our poll question right now is, which dewatering methods are you using the most? Groundwater flow, user definition through phreatic level, or none? So I'll give you guys a minute to answer that. Richard, how do you think most of our users here are going to answer?
I would guess answer number 2, user definition through phreatic level, but who knows?
Yeah. Sounds good. Well, I'll give you guys another few seconds and we'll see what our consensus is. All right, so it looks like you were right, Richard. Good guessing there. So thank you for your feedback, everybody. I'll come back later with a quick poll question. And with all that, I'll hand it over to Richard.
Thank you, Camille. Thank you very much for your presentation. Welcome, everyone, and thank you for joining today's webinar on excavation and dewatering in Plaxis 2D, but most of the comments I will be doing today will be also applicable with Plaxis 3D. I'm Richard. I'm with Bentley as a principal product manager now, and today's presentation will be mostly focusing on dewatering in a particular case of shaft construction, and will be followed by, this time, a relatively short and quick, not demonstration, but presentation of the model, highlighting, I would say, the most common convergence issues that one could be facing when dealing with such type of modeling issues. So just before to get started with the demonstration, I'd like to go through a few topics and some remarks I like to make for anyone interested in using Plaxis for the sake of modeling excavation in general. The first thing I like to talk about is model boundaries. So you could find in books and references a bunch of formulas. I tend to say to the people that you should not be too conservative, I would say, and do not hesitate to have relatively large model boundaries. It's much better to have a large model with a relatively coarse mesh than a too narrow model with a fine mesh. I mean, the consequences could be much more dramatic in the second case than in the first one. So usually, I try to focus on this lens called A in this graph, which is the lens behind the latest structural element, and I would consider this one to be at least 3 times larger than the most the largest structural lens, I would say. This is usually what I do apply. And again, there is a model that you could judge to be too large will not really harm, because the Plaxis measure automatically adapt the reference element size as the size of the model. So a larger model is not necessarily a model that will contain more elements. A larger model will consist of a model with slightly larger average element size, but with the same number of elements. And because in Plaxis, and especially in Plaxis 2D, we are using higher order elements, still the result will be relatively accurate. Mind also the gap and the distance at the bottom of the excavation, over which small strain effect on the stiffness will start developing. So if one is using a constitutive model that takes small strain stiffness into account, you don't need to worry about that. But if you are considering a model for which small strain stiffness is not implicitly accounted for, well, this is something you will need to introduce yourself by introducing that extra layer over half of A, over which you will directly input the small strain stiffness directly as a model parameters. I like to say a few more words about material behavior, which is also quite important for excavation. You are dealing with an excavation problem where you will be facing both unloading and primary loading. And the unloading will be happening in vertical unloading as well as the horizontal behind the wall. So you clearly realize that we are having a situation here where the stress path being followed by the soil will be completely different depending on the location where the stress point is located. And for that, you need to have a constitutive model which is capable of taking this into account properly. Usually, we are advertising to use the hardening soil small strain stiffness. In the sense that with this model, nonlinear elastic unloading, reloading will be accounted for, shear plasticity due to horizontal unloading as well. And most importantly, I would say, compared to the hardening soil model, is that the high far field stiffness will also be accounted for usually better settlement throw prediction. This is something that has been observed. Usually, the introduction of the small strain stiffness further improve the prediction of the settlement throw. The reason why Mont Coulomb is not a recommended model is because it provides unrealistic deformations in the sense that you will observe overestimation over the bottom heave, as well as in many situations heave of soil behind the wall, which is completely unrealistic. And occasionally you could even observe situations where the excavation would widen spontaneously, even without anchors. The reason for that is that the Mont Coulomb model inside the Mont Coulomb failure surface deals with every stress path as an elastic stress path. So unloading and reloading are always considered with the same stiffnesses no matter what. And this is the reason why unrealistic deformations are being obtained. Usually from a pure qualitative point of view, the hardening soil model provides a much better displacement and deformation prediction, with a better bottom heave that would though increase with model depth, and a settlement throat behind the wall which would be much more accurate. And then finally, as I said before, the addition of the small strain stiffness dependency will also improve quantitatively, also the displacement. Of course, this will also require for you to calibrate 2 additional model parameters compared to hardening soil. But this is usually our recommendation. In terms of mesh refinement, well, there is not much to say for this type of problem, as Plaxis 2D does already a pretty good job in defining automatically the meshing. The only thing I may sometimes suggest is when the retaining wall is modeled using solid elements, it might be interesting to, in order to control the number of elements through the thickness, to add, I would say, fixtures line, which do not have any physical meaning, but just for the sake of, I would say, forcing the mesher to mesh along those lines and then automatically increase the number of elements through the thickness. This technique is also called sometimes partitioning, and this is something I do almost systematically use when modeling retaining wall as solid elements. So this is what is being suggested here. Another interesting remarks, still related to the modeling of the retaining wall as a solid element, is the absence of structural forces by default when using such type of modeling techniques. Soil elements and will only provide, as a result, stresses through the wall, whereas you are most likely interested in structural forces along the neutral axis of the wall. So here there would be 2 strategies that could be used there. I am just here talking about one, but I should also mention that now in Plaxis 2D output, it is possible to automatically calculate the integration, the structural forces resulting from the integration of the stresses in such retaining wall by using the automatic center line. Maybe some of you are already aware of that, and computes along that automatically detected center line for the selected soil clusters. In that case, that would only be the retaining wall cluster, to compute the integration of the stresses and calculate the resulting axial forces, shear forces, and bending moment. This is relatively accurate, except maybe sometime for the shear forces. And this would require as well that you would specify enough elements through the thickness. This is also why I've highlighted earlier before a recommendation for increasing the number of elements through the thickness of the retaining wall. There is another technique which I'm still using myself personally from the old time, which consists of introducing a dummy beam, the dummy plate, I should say. I would insert this dummy plate along the neutral axis of the retaining wall, and the only purpose of this dummy plate is to monitor the evolution of the axial strain and change of curvature, which will enable me later on to easily retrieve the structural forces in terms of bending moment and in terms of normal forces. So the idea is to introduce that dummy plate with, of course, a stiffness which will not considerably affect the existing stiffness already taken into account by the fact that the retaining wall has already been modeled using solid elements. So usually I am using, as I would say, a given ratio and once the calculation has been obtained, you could simply start looking into the dummy beam that will provide you here the epsilon and kappa of the dummy beam. And once you have that, if you simply multiply by the true normal stiffness and bending stiffness of the element, you will be, in the framework of the beam theory, able to compute the axial force N and the bending moment M. And how one can easily obtain the epsilon and the kappa simply by considering the ratio of the dummy force, the dummy forces over the corresponding dummy stiffness, as I expressed it right next to it, N over EA dummy and M over EI dummy. And then this is where you start realizing the interest of taking a ratio of EA real over EA dummy, as well as EI real over EI dummy, just for the sake of being able to easily compute the real structural forces from the dummy one. And this is the reason why usually one is using a ratio of 1,000 and sometimes 1 million. So which is what I will demonstrate here. So here the soil elements, as I mentioned, are being modeled using material representing the wall material. Usually here it is concrete in almost all cases. And as I said, because it is difficult to obtain the structural forces, we will introduce these dummy plates. So these dummy plates should not have any influence on the deformation. So it should have a low stiffness and it should have no weight. It should be located along the neutral axis. And we should also offer a tight bonding to the concrete element. So there should not be any interfaces around this dummy plate. And then finally, by doing the mathematics, you could see that you could compute the forces of in the real element by multiplying the dummy forces by this ratio between the dummy stiffness and the real stiffnesses, okay, as I explained before. And this is something I am still using myself personally, although, as I mentioned before, you could also obtain those results by direct integration of the stresses through the automatic centerline tool available in Plaxis to the output. Another important aspect related to retaining wall is the source interaction. Well, I think source interaction is important almost in almost any project. This is the reason why Plaxis is becoming so popular. And Plaxis deals with that using interface elements. So the interface element will handle the normal and the shear behavior between the structure and the soil, usually. In fact, those elements are formulated based on the relative displacement on one side of the interface connected to the soil with respect to the other side of the interface connected to the structural element. And then based on the relative displacement, Plaxis will compute the normal stiffness, sigma, and the normal stress, sigma, and the shear stress, tau, as a function of delta U and delta V, which correspond to the relative displacement of the interfaces. So this will be primarily done using very high elastic stiffnesses of the interfaces compared to the soil. The idea is that we do not want those interfaces to develop large irreversible strain. They should be as small as possible, but we will limit the development of those stresses through a set of failure surfaces, which are being represented on the right-hand side, delimited by the Moore-Coulomb line for the shear and the tension cutoff for the compression part, in tension, I should say. So as long as the stress paths move within those boundaries in red, the behavior will be assumed of the interface will be linear elastic and considerably stiff compared to the soil. So it's such a way that the condition will be almost sticky, correspond to a sticky situation. As soon as the stress path starts moving along those red lines, then we have a sliding situation or an opening situation if you are on the tension cutoff. And that's the way the interface are supposed to be functioning. And of course, the parameters that will control the Moore-Coulomb lines in terms of friction angle and in terms of cohesion, which are the two parameters you need to perfectly define this Moore-Coulomb line, will be by default based on the strength property of the soil in which the interface is embedded times a certain reduction factor, which is being called R-inter, which I will demonstrate here. So this is the way by default Plaxis is computing the properties of the interfaces in Plaxis, you see? And this R-inter affects both mostly the strength, but also the stiffness. But you need to realize that interface properties do not have to be necessarily input that way. It is well possible in Plaxis that you define your own set of interface parameters and assign them directly to the selected interfaces. This is also something which is perfectly possible and acceptable in Plaxis. I will not spend too much time on interfaces behavior in that presentation. I don't think that's the aim of the of this presentation, maybe just to mention that the interface element have now been formulated considering a gap closure feature which has been added quite some time ago, which enforces first the interface to close the gap due to opening through the tension cutoff before being able to retransmit normal forces from the soil to the structure and vice versa. And finally here, give some suggestions about the possible suggested R inter value depending on the type of interaction one is dealing with. Something interesting to know about interfaces still, this is the case of inflexible corner. I mean, this is something that may often develop at this location where the corner are being defined, where you see here at each corner a pair of nodes which are being which belongs to two independent sliding mechanisms, one which is horizontal, another one which is vertical. You understand that this will generate for those pair of nodes a incompatible mode of deformation, okay? And usually during the calculation, this will result in bad, shaky, I should say, stress results, which are moreover inaccurate and can possibly provide artificial additional bearing capacity eventually. One way to circumvent that is to slightly extend the interfaces into the soil, as displayed on the second row, in order to force the sliding mechanism to progressively vanish into the soil. And using that technique, usually one can observe an improvement and a much smoother stress profile around the structure. This is something that we also systematically we are systematically suggesting that you should be doing. So let me now come to the maybe the most interesting part, at least for that webinar. It's called dewatering, and this is most likely what I will talk about for the rest of this webinar. As you may be well aware of, in Plaxis, two possibilities are being offered for dealing with change of pore water distribution. And this is something I will also explain later on and demonstrate. The first one, which is the default one, it's called the phreatic method. It's called phreatic because it's based on phreatic levels. It's in fact a user-defined distribution, which is based on piecewise, I would say, hydrostatic distribution of the pore water pressure based on user-defined phreatic levels. And next to that, Plaxis offers the possibility to also compute pore water distribution field by means of groundwater flow analysis. Steady state most of the time. Transient analysis are also possible, but you need to be working in that case in the framework of a fully coupled analysis. But you also have the possibility to run and to get to update the pore water distribution in your model through groundwater flow analysis. So let me get to that a bit more explicitly. So in case of you are doing dewatering by means of the first method. So usually the first thing you should take a look at is when you define the phase, in the phase settings, you do have a property called, which is being highlighted here with the black ellipse, pore pressure calculation tab on the left part here, you see, and is set to phreatic. This is the place where you start changing from phreatic to groundwater flow, okay? And this is the phase settings. Once this has been done, then you need to be monitoring carefully for each cluster, as defined in the Selection Explorer, the water conditions. And the water conditions here is what will define the water level in a specific cluster based on hydrostatic distribution. So in that particular example, this cluster has been set to dry, which means that water has been completely removed, but in that specific cluster only. And then finally, the last important model parameters you should take a look into is the global water level in the model conditions water feature here. And this could be by default set to the borehole water level, but you could also refer that global water level to any user-defined water level, as I will also explain later on. So this is what you would need for the first case. And this is also what I will demonstrate in the upcoming demonstration. And then finally, what you will observe usually is, as I said, no flow will be really taken place. You will just have piecewise hydrostatic distribution, and where you see that the phreatic level and the piezometric line remains parallel to the defined reference water level. So here you need to have a clear, by using this method, you need to have a clear idea of what what the water level is going to be looking like and how the water distribution will be in your model. If you do not have any clear idea, then we may recommend to use groundwater flow. So in that case, you will first need to change the pore water calculation type here and switch it from phreatic to groundwater flow, and then provide additional parameters to the model, because now the updated pore water pressure distribution will be obtained based on an additional finite element calculation that will be calculated for the water only, based on a mass balance equation for the water. So for that, you will need two additional sets of parameters. The first one will be material properties for the soil in terms of permeability as the first thing you will need to define. So for each material, you will need to provide permeabilities in both directions. And if you are also considering unsaturated zone, you may also need to provide additional retention curves that would describe the behavior of the unsaturated zone in terms of pressure versus degree of saturation and pressure versus relative permeability. So that's one thing. And the other thing would be, of course, like any heavy problem, boundary conditions for the flow problem. All around the model, you need to tell Plaxis whether the boundary conditions are going to be closed or eventually at a fixed head or as a seepage. A seepage, basically, water is free to go through that phase, but you don't know exactly where it will be. And this will be dealt with automatically by Plaxis. But you need to choose among those boundary conditions. And you need to be very careful there, is that by default, Plaxis will always adopt default boundary conditions, which, in my experience, in most cases, are not the one you are willing to consider. Although the default boundary conditions for mechanical part of the problem is always properly and nicely defined, but for flow calculation, no, we are considering that everything is open at the global water level, which is most of the time not what you are interested to consider. So be careful about the boundary conditions as well. And then, once you will run the calculation, you will see that a true water flow will start developing, as you could see here, and you will see that now the piezometric lines start following much more complex shapes, considering the situation, the boundary condition, and the different permeabilities being introduced in the model. So this is how you could potentially perform dewatering in Plaxis, and I will illustrate that further during my quick demonstration. I will be about to start in a couple of minutes. Just a few more words now about identifying convergence issue. And the convergence issue here, most of the time, are not related to the flow problem itself, but more the consequence of changing the water pressure onto the mechanical problem. Yeah. You change the pore water pressure, and you need to realize that Plaxis computes equilibrium based on the total stress. We are always looking for an equilibrium of the total stress between the load and the stress into the soil, in general, as a total stress. And because we are using Terzaghi as a main assumption for most calculation, and the total stress is always the sum of the effective stress and the pore water pressure. And even if you don't change the load, changing the pore water pressure will bring considerable change to the effective stress. And this is what most of the time will cause the convergence issue. And they are quite difficult to identify sometimes. And this is what I'm intending to help you with the rest of this presentation. So there is always a few things you need to be very careful when running a calculation. Is always to take a good look at the control progress windows. This is something people are sometimes overlooking, and it contains a bunch of useful information. And most particularly, the fourth one I have highlighted here. The summum stage, we show that corresponds to how far you are from the calculation. Any calculation always starts with the summum stage at 0, so which means that the introduced unbalance due to the change of configuration between two consecutive phases, has not been solved. 1 means that it has been fully solved. So this summum stage gives you an indication how far you are from reaching full convergence, so M stage is 1, but also the rate at which the calculation is progressing. I mean, if you see some M stage nicely increasing steadily, it's relatively a good sign. When you see some M stage staying at the same number over and over iterations and over steps, that's not a good sign. The other things you should be looking into is the global error. The number 2, the global error is the error you accept to judge whether a given iteration, a given step, would be completed. It's set to 1%. So that's also an indication. The third part is the stiffness parameters. The stiffness parameters, well, it's a specific ratio. In fact, I would say it's an energy ratio. It's the consideration of the elastic work over the total work. The elastic work represents the energy which is stored in the model in terms of elastic strain, and the total work is just the work of the forces being applied, which is stored either in elastic strain energy, but most of it will be dissipated as plastic strain energy. So that's this ratio. When you understand that this ratio gets close to 0, so it means that the amount of dissipated energy, so the amount of the work of the forces being applied is considerably larger than the energy that can potentially be stored internally in terms of elastic strain. So usually, the lower this number, the closer you are from divergence, from non-convergence. Still, soil is meant to plastify, and quite a lot. It still might not be an issue, but usually when you see that stiffness ratio going beyond less than 0.1%, well, usually it means that there is something going on. And if you see that stiffness going further low and low, then you know that you will never converge for that particular phase. The last part you should take a look into are the inaccurate points. It locally pinpoints the area where Plaxis has not managed to solve the out of balance force locally. And usually the inaccurate points will pinpoint the area in the model where convergence is difficult to be reached. So just with this information and looking also into output, which I will do later, you can already identify quite a large number of convergence issues and help you to fix them. So the first thing you could do is to look, as I said, the most important part is to look at the plastic point, you see, and especially the inaccurate one. So you see here two situations where you do have plastic points. You should use as a plastic point, but when you look at the plastic point, you should be most likely focusing on the failure point, and the failure point are the more Coulomb point and the tension cutoff point. So those are the white and the red. The other plastic points are less relevant. They are just there just for the sake of introducing nonlinear behavior. So they are just hardening point. We create plasticity before failure just for the sake of having a nonlinear stress-strain relationship of the model, which is characteristic of soil. But the hardening points are not failure points. So they are not points to be concerned about. The white one and the red one are. When you look at the first, the left-hand side, you see a lot of tension cutoff point developing at the excavation bottom. So which means tension. So most likely here, the soil is failing in tension due to the fact that most likely the water pressure inside the soil is too large compared to what the soil can sustain, compared to the weight of the soil. The second one on the right is different. The failure seems more to be driven by shear, and most likely by shear, as you could see, as the large development of failure point rates seems to be showing. You could also take a look at the summum stage. You could also look at the history of the summum stage in output, under calculation information. So usually this is how you will start pinpointing a situation where summum stage is not moving forward, or even sometimes could go downward, could reduce as a result of the arc length control. I will also come to that later. As well as the relative stiffness, which I also mentioned, could be something relevant to focus on during the calculation. It's also for you well possible after the calculation is done to take a look at the evolution of the relative stiffness in the same calculation information dialog box in output. And this is usually what you should take into consideration when trying to pinpoint and detect convergence issues. So this is the end of my first presentation. I will just now do a very quick and brief demonstration. So we will now be considering, well, this webinar was entitled Shaft, because we'll be doing with simulation of the shaft today. So this representation here represents an axis symmetrical model. And we have a shaft here, which is 30 meter long and 16 meter diameter. And we will try to excavate it like into 20, even 25 meter at some point. With consideration of dewatering, you see the water level here has been placed completely at the top. And we will try illustrating this dewatering here using two different methods. The first one will be the phreatic level, and the second one will be the groundwater flow. So the shaft will be, as I said, will be modeled here by means of solid element. I will not be using plate element. I will be really using a solid element to represent the shaft. And we will be considering 4 excavation level in the first place, to 5, 10, 15, and 20 meter. And the soil model parameters will be just a sand model. We'll be using the hardening soil small strain stiffness here, using drainage type, with the following parameters. So this is I would say the most complex model you could use in Plaxis for representing sand, and this is the one we would systematically recommend if you are aiming at obtaining realistic deformation. So I will now offer you a quick overview of the model. So I will start sharing my screen, and by the time my screen, the time that it would take for my screen to pop up, I think Camille would like to ask you another question. Camille, I hand it up to you.
Sounds good. Thank you so much. I hope that everyone's enjoying this presentation and learning a lot. So we're going to ask you another question here. How often are you facing convergence issues when running a Plaxis analysis? And we have here less than 10%, less than 25%, or more than 25%. So I'll just give you all a moment to answer that. And I just wanted to also thank you for all of the questions. We're going to get to them later and to most of them as we can as time allows. So we have our answers here. It looks like less or more than 25% is our leader. It's pretty close to less than 25%. So that's interesting. All right, and I'll let you run your demonstration.
Thank you, Camille. I think my screen has popped up now. So, well, this is the model. So I figured out there was not much point for us today to go through the entire construction of that model. I mean, it's pretty straightforward. Maybe you see here that I'm highlighting all the recommendation I was providing in my presentation. So you see here the way I have sliced this this cluster here, just for the sake of you see, enforcing the mesh to follow, and this way having enough element through the thickness. I also here included the extension of the interface elements slightly into the soil. And well, this is, in terms of geometry, this is basically it. The material which is unique here has been defined according to what I presented. And initially, the water level, which is defined here, is set at just at 0. Okay, you see it here. And let's take a look now to the phasing. So we have initially the initial phase, which is a K-knot procedure here, and then I will just wish in place the diaphragm wall with introduction of the dummy plate here, the interfaces, and so on. And then I will start dewatering. And the dewatering here is going to be done by iterating over the same sequence of actions, I would say, where I do deactivate the salt cluster and I just set it to dry right here, you see? You see, for each of the faces, you can recognize here with the logo there, for each of the faces, let me show this now, I am systematically using, for pore pressure calculation type, phreatic, you see? I'm not using, so this is what this logo here, the third logo here means, okay? And consistently, I will use this dry. Note that in that case, the pore pressure here of the remaining cluster remain unchanged, still set to global level. And this global level is defined here. In model condition, if you look to water, you see water define the global water level here to be at, I hope you could see it properly, is at set at borehole water level, which is the one defined in the soil module, okay? Eventually, if you want to have a better overview of the water conditions, you could move into flow conditions. And then the model here is the same model, but Plaxis now focuses the color only on the water condition rather than on the soil parameters, okay? So what you see here, you see that everything of this cluster, they points here to global. This one is dry, and I forgot to mention, this one in between will simply consist of an interpolation as I said here, using the option interpolate, a vertical interpolation between the pore water pressure on the top cluster and the water pressure into the underlying cluster. Okay, so it would just like draw a straight line, I would say, between 0 and whatever value will be defined here by the global water pressure. And this is the same I will consistently use over each phases, you see, over and over again. Okay, and this is how I will define my calculation. So for the sake of speeding up the process, the calculation has already been run, but I can tell you the process is very short. It could be run very rapidly, and what you would see is that at phase number 2 here, I already observe a divergence. It's not working. Okay, and well, many people at that stage, well, they start a bit panicking, and sometimes they just stay there. They call a colleague or eventually they contact support. But the first thing you could do here is to start taking a look at output. And taking a look at output will already provide you some interesting results and insights about what's going on. So output will now show up. Let me bring this to you. So this is the output for phase number 2. And the first thing you could start looking into is this. So if you look here into project, you do see this calculation information right here, as I mentioned to you. That was not the correct one. So that was not the correct one. Sorry, it was the last one. Calculation information per step here. And you see here, you have the possibility to retrieve, this multiplier, this sum MSF. Okay, so initially it's set to 1 because those are the first phase, but at some point, stage construction, I was not looking to the right. Sorry, I got a bit confused for some time. I'm really sorry for that. I was not looking into the right. It should be the stage construction, of course. And here you see, so it goes to 1 for the first phase, but this is the phase we are interested about. So the first phase, and well, look at it. You see, it's stay at 5.26. This is for the last phase, and this is for the phase number 6. But for phase number 3, you look at here, it goes to 52, and then it starts decreasing, 51, 50, 47, and 46, and then it stops. That's what you observe here. This phase here is in fact this phase that should not have been run yet, but that I have run in my example, correspond to the next phase, to phase number 6, where I do rerun the same phase, but taking out the arc length control. I will come to that slightly later. But this is what you see here. You see a reduction. So you introduce an out of balance by removing the soil at the second excavation level, by removing the water, and by readapting the water on the cluster underneath through the interpolate. So all of this will introduce an out of balance before compared to the previous phase. And this is this out of balance that Plaxis tries to solve here incrementally. And what it tells you is that it managed to go up to 55.2% of this out of balance. And then at some point, for some reason, it starts reducing the load. Okay, start to go backward, I would say. So this backward, this moving backward thing is in fact controlled by Plaxis, but what we call the arc length control. The arc length control basically starts, well, it's a bit, I can explain that, starts to control the amount of incremental change of out of balance, I would say, such that the resulting incremental displacement does not become too large. This is what it does. And this control does by an arc, I would say. And if you look at the force displacement diagram, it's controlled by an arc. And this is this, for this case here, when you start to have a loss of stiffness that generates large displacement, that Plaxis starts activating and try to reduce the load increment that we are considering. So this is solely due to the arc length. And then next to that, if we go back to Plaxis, we do have another feature here. Let me open and show that to you. In the control here, something which is called the maximum number of unloading steps, which is set to 5, which means that if Plaxis does more than 5 consecutive unloading steps, it will stop no matter what. And this is what it does here. 5 times unloading, I just stop, because if I keep on unloading, I mean, I don't stand a chance to reach 1. Better to stop now, which is good, because you will not use time by waiting sometimes indefinitely for a calculation that will never converge. But I also observe situations for which this stopping of the calculation might be a bit premature, such that the failure mechanism, which is in fact developing, is not fully established. So in that situation, it is relatively still relevant. So let me show that to you. Let's try to look, to take a look at the results. And let's see what we see. So this is what we have here. And you could start looking, for instance, at, as I said, the plastic point, which I say would be, and this is what you see here. So you see a bunch of plastic point here. And what I have here, you see, I am mostly focusing onto so there is no cap or whatever. So those are the points. And if I only look at the inaccurate one, well, this is what I see. Okay, close. I wish I could maybe magnify those. I will do that now. Yeah, so this is what I've done. So those are the plastic points. So this is inaccurate tension point and inaccurate failure point at the end. Well, we know that something is going on here, but it's not yet for me clear enough. And this is the reason why I have recreated that additional phase here, which is exactly the same as this one, with the only difference that I do not have the arc length control on. You see, it's off. So by disabling the arc length control, there is no longer any mechanism for Plaxis to lower the load, and in fact, it will without any control, without any arc length control, the increase of the summit stage can only be steady. And let's take a look at what we obtained in that situation. So let me go back to that situation where we are here, and we start looking into the calculation info per step. We were looking at stage construction, and this is phase number 6. So what we see right now, we see that calculation, no matter what, no step, fixed at 56.2%. It's no longer moving on. It just stayed there. It's like along a plateau. So this is most likely, I would say, a failure mechanism here. I can also try to look into the step information. I was looking whether I would see. Let me retrieve where this. Well, I wish I could retrieve easily, but I don't. Where there it is. Sorry for that. The relative stiffness was, and you see the relative stiffness. So start becoming even negative in that situation. So it starts doing very, very low and even negative, which has no meaning. So negative means it's basically 0. That's what it means. And then look at what we observe when we start looking at the same inaccurate plastic point, but looking into that last phase. And then it becomes clear. I mean, we are forcing, you see, like the soil get into tension here, which cannot be solved, okay? And the reason for that is very simple. We have pore water pressure here, which starts to pull due to the gradient we still have. And here there is no weight, enough weight to compensate. But there is no way you can reach equilibrium, okay? So that's why we have a problem in tension. There is the very funny thing that if you would run the exact same analysis here, but assuming the soil to behave undrained, then it will converge nicely, because this pore water pressure here applied, generated by this by the water level in the soil, will be compensated by by suction into the soil, and we get equilibrium. But here we cannot have suction because we have drain behavior, and this is why we are diverging. Okay, so this was for the first case. The second case I have prepared deals now with dewatering. So I will not save that, and now I will start using dewatering, but with the groundwater flow, sorry. So this is exactly the same model, but now here I am using different techniques. And what you see here is that starting from excavation 1, the symbol here has changed. The icon has changed. It's no longer phreatic level, but it's groundwater flow. And you see, groundwater flow will be used through the entire, for all the remaining excavation phases. So if I look into the phase property, you see that here, under pore pressure calculation type, I have been using steady state groundwater flow instead of. And next to that, I have also been providing for the sand corresponding properties in terms of permeability here, as well as boundary condition. And here as well, boundary conditions are better to see and to define in the flow condition mode. So this is what you see here. From the very first here, I'm applying here a closed boundary. You could see that here, as well at the bottom, and I will do it for all the phases. Here, far away, I am defining seepage, so it will be open to that water level, so which means that this phase will remain at that water level here. This one will remain unchanged. And then for all excavation, as you could see, repetitively, I will use always the same techniques. I will dry the cluster, and I will apply a new boundary condition where I will place the water level at -5. Okay, but now I am no longer guessing about the water distribution underneath here, as I was doing before, by doing first an interpolation and then having all those clusters here remaining as for the global level, because it was not good enough, was a bit too conservative. We expect that in a sand, the hydraulic gradient will considerably reduce there. So I will let Plaxis calculate that through groundwater flow analysis. And you can already observe that convergence behavior is better in that situation. So I will try to show you some of the results still relevant for that case. I'm sorry, we are getting over the hour now. It's taking a bit longer than I would have expected. It's always a bit like that with me. Sorry for that. And so this is the plastic points. So we have a lot of plastic points, but again, we need to be realizing that most of those plastic points here are not relevant. I would like to solely focus on the tension, and you see, and even the inaccurate ones, so they are very limited, by the way. But first of all, before looking into the plastic points here, I like to take a look at the flow results, because so in that case, you could start to look at the flow results here by looking at groundwater flow and Q. So what you see here is the groundwater flow, which is presented here as contour plot of the magnitude, but you could also present them as arrows. And what you see here, you clearly see the flow going through the underneath the retaining wall and intensifying progressively as we are getting here. We can also look here at the water head, of course. We may even look at the hydraulic gradient, but we could look at the water head here. So this is the water head, and of course you could start displaying by doing a cross section here the water head along that line, and see how it defines. Okay. Maybe this is not the water head. Maybe I could also do with the pore pressure. Yeah. So if I would compare that to the previous simulation, you see that here already the pore pressure is much lower than it was initially. It has been considerably reduced, which explains why, by reducing the hydraulic gradient here, it is easier for me to get convergence. But this still being said, it seems like for the last phase, the gradient might become still too large finally here, due to the fact that we have much more water coming in at that stage, and still this phase will not converge. And that's the reason why I have introduced lately a last phase here, where rather than using 20 meter, I was considering pumping the water even lower at minus 25 in order to reduce the gradient, increase the weight here, and have something which is stable, which is going to be achieved. So this is basically the end of my presentation. So I will now go back to the stop sharing my screen and go back to the slides for a few concluding remarks. I need to see the audience view. I push it to audience. Well, sorry for that. I got it now. So a few concluding remarks. So we have been going through two different methods. The first one is the dewatering one using phreatic level. So Plaxis here clearly shows, well, I don't know what's happening. Yeah, sorry. So we have clearly seen here a bottom of lift to do the imbalance between the submerged weight of the soil plug and the pore water pressure underneath at shaft tip depth. So this will maybe not lead to an overall stability mechanism, but the risk of boiling is completely relevant here, and this is what will happen. No, this is for the groundwater flow. I'm really sorry for that. So let me go back to the first model first. I was talking about the second model. In this first example, where water has been modeled through phreatic level, we have clearly shown a bottom excavation failure in tension. And the reason for that was the too large pore water pressure gradients induced by the user-defined dewatering at that location, as I already previously mentioned. And that's the reason why we have reassessed the example by introducing a different and more realistic pore water pressure distribution by means of a groundwater flow calculation. Still good for you to remember here the location of the inaccurate failure plastic point and tension cutoff plastic point, as well as eventually deactivating the arc length control in order finally to force the failure mechanism to further develop and get a better overview of what's going on. Sometimes it's good to force failure to understand what's going on. The second example here, reference results, was the second case. So here the bottom of lift to the unbalance. We have an imbalance between the submerged weight of the soil plug and the pore water pressure underneath at shaft tip depth. So this is what we have observed in phase number 4 in the second case, and we don't think there is a risk here of overall stability, but still we have a risk of boiling. And the solution that we have adopted here was to further lower the water pressure in the last phase. So it's phase 4B. So I am done with this presentation. I will slightly soon hand it over to Camille for the last poll question, to Audra, I guess, for the last poll question. And so for myself, we will come back again for a few Q&A session at the end. So I give it to you, back to you, Audra.
Hi, Richard. Thank you so much for your presentation and your demo. We do have one last quick poll question. So following the presentation of today, would you like to be contacted by one of our geotechnical experts? So in that, you can answer yes or no and click submit. And so while everyone is answering that, Richard, I think we have time for maybe 2 or 3 questions. All these other questions we will respond to through email. We do apologize for not having all of that time, but Richard, if you want to pick out 2 or 3, and
Sure.
then we'll get to everyone else.
Sure. Thank you, Audra. So, well, question which came was the reason why I've been using solid elements instead of plate element. I mean, it's this question that people are asking me. Well, I would say there was different reasons, but we are definitely looking into something here, which is, I would say, relatively thick, and for which I believe end bearing capacity might be of relevance there, and to be honest with you. So this is why. And the second thing is that if you try to evaluate properly passive force and active force on each side of the wall, I think consideration of the thickness, especially for the passive side onto the soil plug, I think it is. I had the feeling it was a bit more accurate to proceed this way. So that's the reason why I have done it this way. No other reason for that. The problem with plate again is the fact that you need to add some specific treatment for dealing with the end bearing capacity. The second question is, though, people ask me, where to use groundwater flow, where to use phreatic. Well, it's a difficult question. Some people say sometimes, well, it's better to use groundwater flow all the time because it is the most accurate way. Yes and no. Yes, it is the most accurate way. As soon as you are convinced that the steady state situation is the one which is relevant for you, there are situations where this might not be, especially when you start working in material which are relatively impermeable. The steady state might not be the most relevant case, and sometimes you might be better off doing a phreatic level using conservative assumptions rather than to be doing a completely unrealistic assessment of the water pressure to be corresponding to the steady state one. So that would be my answer to that question. And then finally, another question was how to evaluate the water discharge at the bottom of the excavation, because we apply a boundary condition, but then people start asking, but how much water do I need to take out of the soil in order to be able to reach such a boundary condition? And I think it's a very good question, which I initially intended to present during my demonstration, but which I forgot. Sorry for that. What I can say is that the best way to do that is to look at the flow. And when you look at the flow, the simple thing you need to do, you remember looking at those arrows that represent the groundwater flow into the soil, just do a cross-section over the width of the bottom of the excavation, just over that length between the symmetry axis and the inner part of the retaining wall. And by doing that cross-section, automatically Plaxis will systematically perform an integration of the water flow along that line. And the integration of the water flow along that line will just give you the discharge in terms of volumes per unit of time. It will be day here. And that's the way you do it. So those are the 3 questions I will have to answer. Don't worry, I've seen here a bunch of questions. I will answer them all one by one when the presentation will be over. Don't worry. If you have some more questions, please do not hesitate to ask them. On behalf of Bentley and myself personally, I would like to thank you for joining today, being always so many coming over and enjoying those webinars. We are very happy for that, and we hope to see you again in the near future. I mean, you need to check us out. We are planning to do many more webinars until the end of this year. We will talk about for that dynamic and source to interaction. So please watch us and see you next time around. Have a very nice day. Bye-bye.